Okay, we're recording. So last time we had just started in on the section on the chain rule. So let me just remind you the broad strokes. And of course, I know that y'all know the single variable chain rule, right? Again, that is not the point to teach you the single variable chain rule. The point is to take a certain narrow, specific perspective on the single variable chain rule so that we can generalize with that perspective in mind. So the big idea is that a derivative can, in this case, should be thought of as a relationship between input velocity and output velocity. Very specifically and narrowly, this is the point of view that I want to take on what a derivative is. It's a factor that you multiply by input velocity to get output velocity. Okay. All right. And specifically, it's a factor. Don't think of it as a fraction. Think of it as a factor. It's what you multiply by one to get the other. Okay. And with that in mind, then look, we found ourselves understanding f prime as this factor that you multiply there, and then g prime is this factor that you multiply there, and so all together, to turn x prime into z prime, we've multiplied by the product of those two factors. And so therefore, this overall factor, the derivative of the composition, is the product then of those two individual derivatives. So that was the point of view we took, broad strokes, quick and dirty. So if you want to, write that down algebraically, then you take this and you plug it into there, et cetera, et cetera. And then here's the pithy little summary, and that is that differentiation turns compositions into products. Okay, so with all of that in mind, let's now do the same kind of thing in a multivariable context. So again, we're going to use what we just saw as a template and see if we can just kind of proceed and make it work in a multivariable context, and it's going to work just fine, as it turns out. So here we go. What is a derivative? Now, of course, a derivative matrix. Right? Ultimately, the natural way to think about a derivative, a multivariable derivative, is it's a matrix. Well, it's what you multiply by input velocity to get output velocity. Right? It's this factor. It's what you do to that to turn it into that. It's just that now, instead of being a scalar that you multiply by a scalar, now it's a matrix that you multiply by a vector. And so, yeah, sure, different context, different details, but I mean, role-wise, right, it's still that the derivative is a factor that you multiply by input velocity to get output velocity. Okay, so let's again look at a sequence of functions, and here we go. Let's see here. We have this function f that takes now several x variables to several y variables. We're going to think about a function g that takes those outputs, the y variables, uses them as inputs and takes them to now new outputs, the z variables. And of course, we can then talk about the composition, right? The process of doing sort of the whole thing all in one step that takes the x variables to the z variables. So again, we have three functions, two functions that are sort of in sequence, and then their composition is the third. And again, let's, you can do this with the algebra, but it's really a lot more intuitive and satisfying, I think, just to think of it again about, look, what's happening at each one of these steps. When you talk about the derivative of f, the derivative of f is the factor that you multiply here. Sure, it's a matrix. Right, fine, whatever, but it's a factor that is multiplied to turn this vector into that vector. And then the derivative of g is the factor that you multiply there to get that, right? It's, again, now it's a matrix factor, but it's just a factor. It's what you're multiplying by what you have to get what you want. So altogether, right, if you ask the question, now let's think about the composition here, g of f of, the x variables. Altogether, that turns the x's into the z's. Altogether, we're talking about a factor that you multiply by that to get this. And, well, we already know that the way you turn x prime into z prime is to multiply by the df factor and then subsequently multiply by the dg factor. Altogether, you multiply by dg times df. So morally, the same idea that we saw here. You multiply by, g prime times f prime, because that represents the two-step sequence when you sort of go along the bottom track, if you will. Okay, so morally the same thing. It's just now it's matrices multiplying by vectors. So we get the same conclusion. And here it is. The derivative of the composition is the derivative of g times the derivative of f. Just want to get the colors right there. There we go. Everybody on board? Notice how it's the same argument. Again, it's really structurally, it's almost exactly the same argument, just applied in a different setting. And yeah, the objects are of different type at this point, but it's structurally just the same idea. Okay. All right. Now there's a few little comments that I need to make here. Little specifics. A lot of students mistakenly, let me hit that button. That gives us more space to work with. A lot of students get a certain aspect of this wrong, and in particular, looking at the DG, why is this DG matrix evaluated at f of a and not at a? So I want to address that. I'm going to segue into that by thinking about the original function f. Here's the act of turning our x prime into our y prime. This is what df does. Df is a matrix consisting of partials with respect to x1, which have to be evaluated somewhere. Where do I evaluate df? Well, I evaluate df wherever I actually am, right? And at this moment, when I'm talking about df, at that moment, I am here. I am at that point A. So df is evaluated at the point A. That make sense? So it's the same deal when you're talking about dg. Here's dg. dg turns that vector into this vector. dg is a matrix consisting of partials with respect to y1 and y2. It's therefore a matrix whose elements are expressions that are in terms of y1 and y2. And where should that be evaluated? Well, it should be evaluated wherever you actually are. And at the moment in question, in this y world, I am not at the point A. You'll notice, right? A is way over there. I'm not going to evaluate a function of y and plug in x values. G has never heard of x, right? G never touches x. We evaluate G and everything you do with G at the values that are actually going into G, and that is this point here, this being the output from F, namely it's f of A. Does that make sense to everybody? Is everybody on board? A little subtlety, a lot of people get that wrong. Easy to mess up. Okay. All right. Okay, next thing I want to talk about. There is a pretty confusing thing on the screen here that even at a glance might look like a mistake, and that is the order that I have F and G. It just looks like I've contradicted myself because check it out. F is on the left here, G is on the right. But wait a second, in the composition, G is on the left and F is on the right. So what gives? So, okay, yeah, we've seen something kind of like this before, right? When we were talking about second partials, and you remember the notation for second partials, it looks backwards depending on which notational choice you make. And ultimately that was because of some arbitrary notational choices we had made earlier. And the exact Same thing is going on here. This g is on the left because that's how we write functions, right? Specifically, think about what g compose f means. G compose f applied to some value x, let's make it a vector, is literally g of f of x. And so you see the notation. I guess I'm a little uncomfortable with the fact that that these are out of step with these, but I think it would be even worse if these two were out of step with each other. That would just be, that's unthinkable, right? Everybody see the, so we are painted into a corner. There is no getting it all right, getting it all consistent here. There is just unavoidably, just because we write functions on the left is what kind of does it to us. So, and they're not going to get rid of that. There are those who would like to change this, and I've actually seen some people will write f of x like this. And if you do this, then that problem goes away. And that would be nice. But it's also really weird and not going to happen, and no one will know what you're talking about when you write that, and it's just, it's too steep of a price to fix what is ultimately too small of a problem. So keep that in mind. You do have to pay careful attention to which way the things are going, which one's first, which one's second, and think carefully about how to represent that accurately in the notation and then how to interpret correctly from the notation. Okay, last little comment here, and this is again just while we're at it, what I've done here, right? The pictures that I've drawn and the implied case that we're considering. There were two variables here, and two variables there. How does it change if maybe the one in the middle has three variables? Is that going to change the formula? Is it going to change the result? And here's the beautiful news. No, it doesn't change it at all. In fact, notice the fact that there were exactly two variables at this stage and at each of these three stages didn't show up in the algebra at all. Right? You look at the result. I guess it's hidden. You might say it's hidden inside of the shape of these matrices. Sure, right? How many rows and columns? Yeah, right, fine, right? But using matrix notation, it just disappears inside of the notation, right? So that's the beautiful thing about it. Even though we were visualizing this all in 2 dimensions, this result applies no matter how many dimensions you have at no matter which stage of these this progression of functions. So cool. Is everybody okay with that? Okay. So again, as we previously discussed, differentiation turns differentiation turns a composition into a product. Now a product of matrices. Okay, so let's do one. Let's see here. Here is our first example. There's a bunch of given. My functions do like this. F takes 2 variables in, 3 variables out. The inputs are called x's. The outputs are called y's. G takes 3 in, spits 3 out. The inputs being the y's, the outputs being the z's. And notice, as I have it set up here, what comes out of F is what goes in to G, appropriate to the fact that we're composing them. Okay. All right. We are given that these are differentiable, so that's, we kind of need that for any of our derivatives to actually make sense, right? We need that. And then we're given these other 3 pieces of information that we'll may or may not be able to make use of as we work the question. So the question that's being asked now, there's 2 questions being asked. First, we want to compute that composition derivative. And second, we want to compute this specific partial derivative. And we'll come back to that second half of the question in just a minute. Let's focus for the moment on this first half. Okay, so that derivative, we just write down the chain rule. Derivative of composition is what we've been asked. We write it down as the product of the corresponding individual derivatives. Chain rule doing the heavy lifting for us. Okay, now we've got to figure out how we're going to find these various matrices. I'm going to need the DF matrix specifically evaluated at the point 1, 2. And good news, that was given. I don't have to take any partials. Good thing I don't have to take any partials. I don't know the formulas for these functions, right? But evaluated at 1, 2, we have the DF matrix given. So that is just this matrix right there. Everybody good? All right, now a little bit more confusing for the other side here. We're going to need, let's see here, let me erase all that. Here we go. We're going to need DG, apparently evaluated at F of 1, 2. Now, that's just copying from the previous page. Again, you can't evaluate the DG matrix at 1, 2. 1, 2 is in a completely different world. G doesn't apply there. It doesn't make any sense. Okay, so is that what we're given? Well, at first glance, seemingly no. We're given DG at the point 3, 1, 0. So how do we, oh, good news, lucky break, F of 1, 2 is 3, 1, 0. So even though it didn't immediately present itself as such, where we need our DG to be evaluated conveniently is where the DG we're given was evaluated. So, yeah, how handy. Everybody good? Okay, so this is actually this, and thus that. All right. Now, I want to point out something that I did in writing this example. I did this on purpose. Some students would call this a trick question. I think that's fundamentally wrong. A trick question is a question whose intent is to trip a student up on a relatively meaningless point. That is absolutely not what's going on here. Here, I wanted to see which students are aware of the very significant point that we talked about on the previous page, namely which direction, which one's on the left, which one's on the right, and you'll notice that I gave the function f on the left, but its matrix ends up on the right because that's where it has to be. And the function g, and likewise its derivative, I gave you on the right, but it needs to go on the left. So please don't just take the functions as they're written on the page arbitrarily and assume that that means something, because of course it doesn't, right? So this is not a trick question. This is a question that requires students to understand a significant point about what is this composition, what does that mean, and therefore which one needs to act first, and therefore which needs to be on the right or left. That's all important. Does that make sense to everybody? Nevertheless, this is an easy one to trip up on and get it wrong just because of how it's written. Okay. Alrighty. So then arithmetic and boom, answer, and that's what our composition derivative is right there. Okay. All right, now let's look at the second part of the question. The second part of the question says, let's see if I can fit this all on. There we go. Second part of the question says, what is this partial derivative? Specifically of z3 with respect to x1. Well, this is the derivative of one of the composition outputs with respect to one of the composition inputs. So this partial derivative is an element of the composition derivative matrix. It's going to be somewhere in this matrix. It's one of those numbers. Everybody all right with that? Which one? Well, check it out. We're apparently looking at the partial of Z3. Z3 is my third output. Remember, outputs correspond to rows. So if I'm looking at the partial of the third output, the number I'm looking for must be in the third row. So it's got to be one of those two numbers. Analogously, notice our partial is with respect to x1, which is our first of our two input variables, which means that the partial is going to be in the first column. So I'm looking, apparently, in this matrix, I'm looking for the number which is in the, let's see here, first column, third row, and that makes it this value right here, which is 3. What do you think? Everybody all right with that? So really important to recall that individual partial derivatives, as they show up in the derivative matrix itself, the input variable tells you which column, the output variable tells you which row. Okay. All right. Okay, so moving along, we have a couple of special cases. I'm actually kind of torn on how to present these. This is actually stuff we already know, but I think it's interesting to just notice that this brand new chain rule actually reproduces, gives us a different point of view on, you might say, results that we already know, stuff from 2.3. This actually goes way back. So here's how the special case works out here. Let me start by zooming in on this part. Notice in this special case we have just the one input variable. So this is a composition of two functions, right? We've got the first function and then the second function, but only one initial variable. So what does that do? How does that show up in how the chain rule gets written down? Well, let's think about this function here, our first function. We have position in Rn is a function of a single variable. Position is a function of time, we could view it as. This is a parametric curve. And we've already studied derivatives of parametric curves. Right? Derivative of a parametric curve is the velocity of the parametric curve. So, in fact, then, and you'll notice, again, one column because there's only one input variable, and sure enough, this is literally the velocity of a parametric curve in Rn. Is that cool? Okay, now let's look at the composition. The composition, and keep in mind the composition, actually, let me get rid of all that. The composition goes like this. The composition gives me position in Rm as a function of, again, the one variable, which I can view as time. So what I have here, the composition is another parametric curve. And again, there being just the one variable, I have just the one column, and recalling from section 3.1, the derivative of a parametric curve, the derivative matrix of a parametric curve is the velocity of that parametric curve. Okay, so what we have then, here's our chain rule, right? All I've done here is write down the chain rule. We only have one column each in two of these three matrices. They are velocities, and so really what this is telling me is that the derivative of this function, right, this derivative matrix of that function is telling me how to take a velocity in Rn and how to infer from that a resulting output velocity in Rm. And again, that's old news. This is something we saw back in section 2.3. Right, this is one of our early interpretations of the derivative matrix. We pointed out that the derivative matrix turns input differentials into output differentials. And then you just divide by dt. And it turns input velocities into output velocities. So this is just, like I say, it's a different point of view. This kind of revisits that old fact. And said differently, that point of view could be thought of as a special case of the chain rule. Now again, this doesn't give us new computational abilities. So I think this example, I'm really thinking about reorganizing this example and literally putting it back into section 2.3 because it really ultimately is a section 2.3 example. In this discussion, the setup of the question, we're given an input velocity and the question is to compute an output velocity. So, I mean, yeah, that's what the derivative matrix does, right? The derivative matrix for f turns my input velocity, which is given there, and it turns it into my output velocity that I've been asked to compute there. How are we doing? Everybody okay with that? I'm skipping over the little computational details. I mean, you do have to take your formula for f up there. You do have to take the appropriate partials to generate your df matrix. You have to plug in the appropriate point. Namely, you have to evaluate everything at A. Again, given over there. And, plug in those values, et cetera, to find that matrix. And then it's just multiply. Everybody happy? All right. Here's another special case. Again, this is not news. This is just a different point of view on stuff we already know. We've previously talked about this special case where you have just the one input variable. We know that means there's only going to be a single column there and a single column there. But now notice, furthermore, we have a single output variable. Just the one output variable, which tells me two things also. That tells me that this matrix has a single row, and it tells me this matrix has a single row. So in fact, if you think about it, the composition here, notice the composition has one input and one output. That composition is a Calc 1 single variable, just regular old plain old boring function, and its derivative is just the scalar, in this case dy dt. Okay, so that's, again, a special case of a special case. Now, what does this buy us? Well, I mean, we have this old observation that when you're doing a matrix times a vector, if that matrix has a single row, that is morally equivalent to doing a dot product with what you might call the transpose, if you're so inclined, if you reasonable point of view anyway. Arithmetically, this matrix times that vector, this vector dot that vector, it's the exact same arithmetic. So the other takeaway from this special case is that when you have one original input variable and one eventual output variable, then this the chain rule just reduces down to, dot product with the gradient, pretty much. It's another nice special case, another old news, another section 2.3 previously known fact. Everybody good? So again, another example that really is several sections too late, arguably. I mean, we totally could have done this example and thinking about moving it around so that we'll literally see it. But a 2.3 example where we have exactly the above scenario. Notice I have a real valued function here of 3 variables. So one output from this function. And it's being evaluated along the path that this bird moves, and the path that that bird moves is a parametric curve. So we have one input, namely time, that determines position where the bird is flying, and from position we infer temperature, which again is a single coordinate, and so thus a real valued, single output, eventual output. So per the previous page, the gradient, dot product with the gradient is how you turn the given input velocity into the requested output velocity. And you got to take some partial derivatives and plug in the appropriate point. Algebra, arithmetic, etc. But the highlights, the big ideas are as noted there. Everybody okay with this? Does everybody see how this is, really literally just using ultimately a fact that we knew long ago, I guess last week, whenever we did 2.3, I remember. So this is really just a rehash of old ideas. All right. Okay, moving along. So there are different ways to present the chain rule. I like to start with this point of view back here, because I think ultimately this is the most natural way to think about the multivariable chain rule. I think it's really most natural, if you have a multivariable function, to view it as such. Look, I have several input variables, I have several output variables. More to the point, this function, where is this function evaluated? It's evaluated at that point. It's a point in space. It's also a couple of coordinates. But it's a point, most naturally, most fundamentally. The coordinates are just how we choose to talk about that point. Right? Let's talk about the temperature function. Right? Temperature in this room. If I want to know the temperature there, at right there, what's the temperature right at this point right here? That's a point. I guess we could say it's a list of 3 coordinates, but that would depend on where do I set up my origin, which is the x-axis and the y and the z. It is truly and naturally should be thought of as a point. The coordinates are a kind of a convenience if it's convenient, but it's not fundamentally what it is. So this point of view on the chain rule is, I think, fundamentally natural. Functions are evaluated at points. Displacements are thought of as vectors. And this takes all those, what I think are natural points of view. Okay, now all of that said, here's a different point of view, which has its moments. This is useful sometimes. Suppose I have composition of functions. Here's a first function. Here's my second function. So the output from F is the input to G. So I can talk about composing them. And with all of this set up as so, I can write down the chain rule, and the chain rule looks like this. So notice all of the partials of the y's with respect to the x's. That's the DF matrix. All the partials of the z's with respect to the y's. That's this matrix. And all of the partials of the z's with respect to the x's. In other words, the partials in the composition are this matrix right there. So all I've done is recopy the chain rule and just, kind of turn up the zoom on the microscope we're looking at this with, so we can see the elements on the inside, right? So now we're just looking at those individual elements. So with this all having been set up, a reasonable question comes up: how would I compute a particular element of this composition derivative matrix? How would I compute? Forget about all the others. If I just want to know just this one partial, how would I compute that one partial? element of a matrix, row dot column. Right? So this is going to be the dot product of these with those. Right, so whichever ultimate output I'm interested in the partial of, I look at its partials with respect to all the y variables. In other words, I look at the corresponding row. Whichever initial input I want to take the derivative with respect to, that tells me which column I pick out over here, namely with respect to which x variable I'm taking the partials of all the y's. Okay, so ultimately then, the matrix form of the chain rule gives rise to what I'm going to call here the coordinate form of the chain rule. Namely, if you just want to know partials of individual coordinates, this is how you do it. And you'd be surprised. I mean, this is actually pretty useful. Very often, you really only need one of the partials. You don't need the whole matrix, right? And so why should you have to spend a bunch of time, let's see here, why should you have to spend a bunch of time computing all this stuff up there and all this stuff down here and all of this and all of that when you're not going to need them, right? If you just want to know that one partial derivative, just compute only and specifically the partials that you need. All that other stuff would just be spinning your wheels. Is that cool? So this formula has its very nice uses. I do want to point out a potential danger with this formula, and you're going to notice if I look just as at the process of writing this formula down, I write this. And it's equal to, and then I write down the first term. Keep in mind, all of this comes out of the matrix multiplication. Right? I need all of these terms. But once I write this part down, I kind of feel like maybe I'm kind of done. I mean, look at this. It would seem like that and that, don't they kind of cancel? And doesn't that give me then the partial of zi with respect to xj? I mean, it really looks like it ought to work. And yet this is wrong, right? It's really, really importantly wrong. We've already agreed, multiplying out those matrices, we can't just stop there. We need all of these terms because that's how matrix multiplication works. Okay, so clearly this is wrong, but why, right? What is it that makes me not able to cancel those partial y's? Again, I claim this is absolutely wrong. You can't do it. Why not? And the reason why, sadly, has to do with notation. This can't be fixed in any way I've ever been able to figure out, in any feasible way that I've been able to figure out. But even though it looks like it, this and this are not the same thing. They're just not the same thing. These are participants in two entirely separate scenarios. Players in two different stories. Let's take these one at a time. What story is going on when we talk about this partial y1 down here? This partial y1 is part of a story where we're interested in how zi is changing, and I want to know how zi depends specifically on that one y1 variable. And so in order to compute this partial, very specifically, I have to fix all of the other y coordinates. In this green story here, other y variables are not allowed to change at all. They do not change. Okay. All right, now let's consider, what about this thing right here? I shouldn't use the same color. Let me use orange. What about that thing right there? Different story. Let's look at this partial derivative that it's part of, apparently. This says I want to know how y1 changes as xj changes. Okay, that means I've got to hold all the x variables constant except for just xj. But here's the thing. If xj is changing, that xj changing will cause all of the y variables to change. Right? If you change the inputs, the outputs are going to change too. So in this story, the y variables are not constant. These are incompatible scenarios. So even though tragically we use the same notation to represent these, I mean, both of these are kind of representing how much y1 is changing, but again, in these very different scenarios. They're incompatible with each other. You cannot be describing a single story here. Even though we use the same notation to represent them, they are not the same thing. And there is no cancellation. Is that cool? Okay. So yeah, you'd be surprised how often I see on exams students who will write down just this. They'll leave off all the remaining terms, and of course that's just garbage. I mean, and again, from a notational point of view, I can see why they would make that mistake, but it unavoidably represents a fundamental misunderstanding of what these things are. And it's just, it's hard. It's real hard to give partial credit in a situation like that. Yeah.
Could you explain again why, for the first, I guess, term, they would need to be constant?
So why the y's have to be constant when we're looking at that right there? Yeah. So that's just what a partial derivative is. If zi is a function of all the different y variables, what we mean by partial derivative is I want to allow only y1 to change, and that means that the other y's can't be allowed to change. They have to be constant. Yeah. That's just what a partial derivative is. Yeah. Okay. All right. Okay. So, how do you in general, how do you think about this? You might be worried that in order to use one of these formulas that gets right to the point of that one partial derivative that you need. Okay, apparently I'm going to have to write down the whole entire matrix form of the chain rule and infer from there. And good news, you don't have to. Here is a different way to think about it. I'm a big fan of this point of view. And that is to draw this little diagram here. Whoops. Draw this little diagram. Notice that this represents my first function in the composition that turns x variables into y variables. And then the second function in the composition turns those y variables into z variables. And this kind of, I'm going to say, represents all of the action of that two-step process. And with this in mind, let's now just ask, okay, fine. If you want to know the partial of that with respect to this, I mean, how you when you change xj and hold all these other x variables constant, how are the changes in xj going to cause changes in zi? And I point out that these changes in xj will propagate along various paths. So in particular, as xj changes, that's going to cause y1 to change. Among other things, right? We'll talk about those other things later. But for the moment, as xj changes, that will cause y1 to change. And furthermore, those changes in y1 will cause changes to zi. Right? So there's kind of a two-step process along this path I have in green where changes in xj can propagate along and cause changes in zi. And check it out. That represents this term right here. The very first term in our coordinate chain rule right there just represents this path through y1. Et cetera, et cetera. Here's the last one. Let's see, I guess I can do this in blue. The last term, as xj causes y1 to change, and y2, and y3, etc., etc. xj also causes ym to change. And those changes in ym will also contribute to changes in zi. And notice that gives you that term right there. So the beautiful thing about it is all you have to do is look at all these paths. Each path corresponds to exactly one intermediate variable. That intermediate variable tells you how to write down the corresponding term. Right? So now again, we were looking for partial of zi with respect to xj. As previously noted, those go, kind of there and there. The intermediate variable in question goes there and there as if we would want to cancel it, which of course you can't. But that's how you write all these terms down. And this proceeds all the way along. So partial zi with respect to xj, then this is what the ym term looks like. All right. It's a really handy point of view. Notice I didn't have to write down the matrix. I can just kind of have this little, what I like to call the road map of how, what are all the different ways that you can get from here to there, and then each path corresponds to a term. Okay, here's a specific example. Let's suppose that we have f and g given, like so. Notice that what comes out of the f function is what goes in to the g function. I'm going to represent all of this with my intermediate variables y1 and y2 by representing how those depend on the x's, like so, and how the z's depend on the y's, like that. Everybody good so far? It's just kind of, drawing a diagram, I like to call it a road map, a little diagram representing the connections between the various variables implied by these formulas of, f and g, take what as inputs and give what as outputs, etc. Okay, so with that noted, note the question here is to compute the partial of z2 with respect to x2. Okay, wait a minute. z2 is my second output variable. I want that partial, let's see here, z2. I want that partial with respect to x2. x2, you'll notice, is my second of three input variables. And so looking at this diagram here, the partial derivative that I'm interested in, how can x2 influence z2? Well, there's two different paths. And this first path that goes by way of y1 gives you what you might want to call the y1 term. And this second path that goes by way of y2 gives you this y2 term. And there you go. No fuss, no muss. I didn't have to write down any matrices. Just keep track of what your intermediate variables are, what depends on what, and boom, formula. And then you compute the appropriate partials. For example, let's see here. Let's do this one last thing, and then we'll call it a day, assuming that clock is accurate. Oh no, but it isn't. That clock's trying to fool me. Okay, still real quick. What is the partial of z2 with respect to y1? Okay, well look, here's z2. z2 is that function. z2 is y1 cubed. And so that partial derivative is just 3y1 squared. So you got to crank out a couple of partials and plug in some values, blah, blah, blah. But easy formula. Okay, all right, that's a good place to draw the line for today, and we will pick up here on Monday, actually. So don't forget we have an exam. Exam 1 is on Friday. Good luck studying, and see you then.
Sorry. That was an inside thought. Yeah, I did.
That's funny. Yeah. All right.
I just want to double check. The exam is